All right. Hi, everyone. Welcome to Chapter 9. This is our final lecture. This chapter is not going to have much of a quantitative element to it. Instead, it'll be more learning some terms that you would need to know if you were to move on into a position that requires analytics of any kind. We're going to talk about taking data and using it more effectively. And let's just get right into it. So this chapter is called Predictive Data Mining. We've got some terms to know. First is observation. We've talked about this. You've seen this, but this is just any record. This is all the variables associated with one record in your log. So if you had, like we've seen in several of the chapters where we did regression analysis on them, what you had was, a classification of, on this visit, you had this repair person, this repair type, or whatever it was, but you had one set of multiple variables associated with this one instance of an occurrence, right? So that's an observation. The number of observations would be the number of rows, essentially, in your table of data that you've collected. So if you ever see observation or N, the lowercase letter N, when it's associated with this, the N is going to refer to the number of observations. Supervised learning. So in machine learning, there's a term called supervised learning, wherein you are feeding the model a set of data specifically, and it's a way to build your predictive model, whatever that model is, whether it's a machine learning model or something you're creating yourself and using a solver tool or the regression analysis tool pack or whatever the case is. Supervised learning just means that there's a person behind it effectively. We often are going to try to estimate something. That's the predictive data analysis. So an estimation of a continuous outcome, meaning there's multiple values that could arise, or we're trying to classify something. So classify the likelihood of one specific outcome from a set of possible outcomes. This could be a binary variable we're trying to predict whether it's going to rain or not, for example. Several steps in the process of data mining. Data sampling is going to be the first one. We're not going to get through this entire chapter, really just the first maybe half to 2/3 of it, but we will cover this whole part. So data sampling, when you're trying to do a prediction of a forecast of some kind, you're not going to usually pull every single bit of data available of a population. If you're trying to predict something for marketing purposes, you're not going to get survey information or data on every single person who lives in Oklahoma. Instead, a sample of people that represent the population are used, a sample set of data. It needs to be large enough that you're going to get something of significance, but small enough that it's workable, right? We're not going to have, whatever the case is, a million people, right? We're not going to have a million people in our data set and have a million lines in Excel. But we might have a few hundred, and then we use that to make inferences on the entire population. The data can be collected in multiple different ways. There is random sampling, where it's literally just, no rhyme or reason to it. You're just grabbing people's information, doing surveys, sending out mailers, and whoever you get the respondents from, you're selecting the first 400 or whatever. You might section it off into various groups. You might say in a school system, you might pull one classroom from each grade and see how that makes inferences on the rest of the students in that grade. If it's high school, right, you take one classroom of 10th graders, 11th graders, 12th graders, and you analyze that information instead of getting data from every single 10th grader, every single 11th grader, et cetera. ideally, you're going to pull every possible variable you can think of, everything you can get a variable on that could conceivably contribute to analyzing the information. And then after you perform something like regression or whatever other type of analysis, you can see which of those variables are actually contributing in any way to your model. Is this helpful at all? If not, we eliminate all instances of that one variable and refine the model. You don't want it to be overly complicated, but you also want it to be rich enough that you can, get some valuable info from it. So data partitioning. So we have pulled all the data, right? But we're going to create for ourselves several sets of the data. We have, as you can see here, there's an abundance of data, right, out there, and we're going to simplify that process. But what we don't want to do is what's called model overfitting. So what happens there is that basically you have all this highly detailed information, but it only works within the model itself because it's so specific to just this set of data only. And then if you apply a new set of data to it, it doesn't work the same way. You don't get the same accuracy on your prediction because it's so specific to just the first set of data that you used. So one way you do that is basically you split the data into 3 sets. The training set is what you use to initially build whatever the possible models are. So you use one set of data and you create a series of models. And then whichever model is the most promising of those, you run it again with a new set of data. That set of data is called the validation set. Now, did you get similar outcomes to that? And maybe you do that to like a couple of them, right? So you narrow your candidates down. And once you've run the validation set, whichever is more accurate seeming, then you use your test set on that once again to ensure that you're getting similar predictions. Your forecasting matches up similarly with your whether it's your regression equation or whatever else you're using to try to do your forecasting or whatever it is you're trying to gain from it. Is it still working as intended? So basically it's 3 sets and you narrow it down from as many models as you can think to build with whatever combinations of variables you want to include, narrow it down to the most promising ones, run it again. The most promising of that, you run it one time with a 3rd set of data. But it helps to ensure that you didn't create a model that only works for one set. It has additional use in the future. After that, we want to see how accurate we are. So one thing you can do is you can test whether something was predicted to be in one set of data or another. So this is when you have maybe like a is what's the likelihood of a defective product, for example. Based on the amount of time it was being manufactured, based on the material, based on the whatever, what's the likelihood of a defective product, right? And so it's going to predict for you. You make a little 2x2 table where you have in one column you have your what was the prediction. We forecast that the outcome would have been 1. Meaning maybe it was accurate or maybe they defaulted on a loan, right? So let's use the example, I believe it from your book. I believe it's in table 9.1 in your book is where this comes from. Oh, there it is right there at the top. Of course, I believe it's table 9.1 because had I looked at the screen, I would see table 9.1 right here. Table 9.1 is talking about loan defaults. So if it was predicted to be class 1, from the model we set up, it was set as class 1. We put it in this column, and then 1 would be that the person defaulted on their loan. Class 0 would mean they did not default on their loan. And so when we have the prediction, we can go back to the actual data and see, based on the model, it predicted that they defaulted, but did they actually default, right? So one instance of so out of all the predicted defaults, these two added together is how many was predicted to default. 146 of them actually did default. 5,244 were incorrectly classified as defaults, right? And then here, how many times it predicted no default, right? These added together are the number of times that it predicted they would not default. And it was accurate 7,479 times. It was predicted 0 and it actually was 0, right? So there's definitely something not great about this model because it's not classifying. Ideally, we would like to see this bottom right number be high and this top left number be high, right? So this one we want to be high because it's predicting 0 and it was 0. This one we want to be high because it's predicting 1 and it was 1. And again, we're talking binary variables. It's this or that. And in this case, this or that is whether it's defaulted or not. So if we use this simple formula by, and if you look at 1001, right, you're just talking about predicted actual, right? So percentage of, it was predicted 1, but it actually was 0. Added together with the predicted 0 actually was 1. So you're adding these two together and you're dividing it by the sum of all of these observations, right? That's what these 4 things are adding up together on the bottom. So, right, if we do this, we can get the error rate. And in this one, it's not ideal, right? Because we had just a ton of predicted 1 when actually it was 0s. This is not good for our planning. We're thinking that all these people are going to default on their loans and then they didn't actually, right? That's not great if you're trying to plan the model. So accuracy is going to be fairly low on that. It's called a class 1, sorry, right. The outcome of classifying something incorrectly can be more or less devastating to your business, depending on what kind of businesses you have. But if you predict that something actually is good, let's say we're predicting a defective product, for example, you're predicting it's defective and it actually was not defective, okay? Well, the harm there is that you're going to probably scrap that product. It's coming off the line and you predicted based on certain parameters that it was going to be defective, so you throw it away, or right, or you scrap the material and maybe you lose some of it and scrap some of it, you're able to rework, right? Ultimately, though, in that instance, you've got what's called a false negative, right? Classifying it as class 1, right? Let me put my laser pointer on. There we go. So you classify it as class 1. So it actually was class 1. It actually was good, but you said it was defective, right? So we'll say 1 is good in this case, 0 is. So a false negative means you thought it was no good. A false negative is gonna likely cause you to have, in this instance, if you're classifying them as positive, negative in that way, monetary problems, right? You've wasted time, resources, you have to rebuild a product, right? But let's think about what would happen if you were to say it is good and it goes out to the public. Now you have the public with a bunch of instances of this product that are actually defective. You thought they were good, so you sent them out. Well, now you have potential liability from harm that might have happened from this defective product. You have the loss of public relations, brand imagery, because you've put out all these defective items. You have the worry about the cost of all the refunds and then replacements. So not only did you rebuild it anyway, or replace it anyway, now you've got extra shipping costs. You probably maybe have to do a partial refund. So what you don't want to happen is sending out a defective product by classifying it as good when it actually is bad. That's definitely much more costly in the long run. We can judge them with class 1 error rates, class 0 rates through this simple formula by just simply dividing the number of times we predicted 1. So we predicted 1 and divided it by the number of times that we predicted one, whether it was outcome was positive or negative. After all, we can check our class 0 error rate by doing the same thing. We predicted zeros, so zeros in the first spot, and we divided it by both the times it's zeros in the first spot. A lift chart, this is going to be similar to what we did when we looked at the basket analysis, grocery basket data, where there is a certain amount of increase to what's happening. We list everything out in order of the probability of it being in class 1, and we'll compare that to the actual, but we do this in a randomly selected way. Let's see, what else we want to cover from this. So that 2x2 grid, if you see the term confusion matrix is this 2x2 grid. There are additional analyses you can do. Again, we're not going to cover the quantitative elements of it. Just know that we would, well, we're not going to do a problem set over it, but you might have some questions on your book as far as processing a class 1 error, class 0 error. So I guess I'll revisit this real quick. You likely will need to know these two formulas, class 1 error rate, class 0 error rate, and you'll need to know the overall error rate, right? So those you will need to know either on your quiz or on your exam, but we're not going to be doing those in Excel for problem set reasons, so we're not going to cover this next chart too closely. Let's see what else we need to cover here. Should have probably taken some of these slides out, huh? It's the end of the semester, guys. So yeah, we're gonna skip over the lift chart stuff because we're not going to cover that at all. All right, sensitivity and specificity are the terms we use to determine how well did we accurately predict class 1 observations. So 1 minus the error rate is our sensitivity. So if our error rate is 25%, when we run this formula, we had 25% error. 1 minus 25% is basically the number of times we got it right. We're taking the inverse of 25%, so 75%. And then specificity is just the term used to determine how often we correctly predicted a class 0 negative observations. Same thing, you find your class 0 error rate, you take the inverse of that, so 1 minus the observation rate. Precision, so specifically how many times did we predict a class 1 that actually is in class 1? So not error rate, because you're not looking at the times when you predict all the times you predicted class 1, but this includes the times you predicted class 0 and it actually was class 1. So basically, if you look at this N1101, the first number in these, just to clarify, first number is what you predicted, the second number is what it actually was. So precision is everything that actually is 1. So predicted 1, meaning 1 comes first. Everything that is in 1 ends in 1. So 1 is predicted 1 and ends in 1. And then 1 and 0 both end in a 1. So they're the times that it actually was a 1. That term is called precision. And then the F1 score sorts the precision and sensitivity into a single measure. So this is every instance of was predicted 1, predicted 1 and actually was 1, right? So it starts with 1, ends in 1. And then the bottom of this is 2 times the number, it's 2 times the number of that, divided by 2 times the number of that occurrence, plus all the times you either predicted 1 or it was 1. So everything that has a 1 in it is added into it. That's called the F1 score. Different ways we can measure our accuracy. These can be mapped out on grid in some way to visualize it once we have the observations, but otherwise we just usually use our decimal point answer for these. Average error, root mean squared error. These are ways to find our error. Why would we use one versus the other? Well, if we have an error, sometimes it's positive, sometimes it's negative. By squaring the error, it removes the negative. So we could take the absolute value, and a lot of times we do use the absolute value. The absolute value of a number just means you don't look at positive, negative. It's just treated as a number itself. So negative 481 is just 481. It's neither negative nor positive, effectively. I mean, well, effectively it is positive, right? I think technically it's neither negative or positive. It's just the number existing. But squaring it, if you take a negative times a negative, you get a positive number. So that's one way to remove that. Easy way for older computers to have done this model is to just say the number times the number itself. Whereas absolute error wasn't as easy to calculate on older computers, so it's kind of a byproduct of that. It also helps to smooth out the errors a little bit as well. We use this root squared, the squared errors as part of our calculation of determining how well the model worked. Logistic regression is a form of it's linear regression if you could do that with a categorical outcome variable, meaning a 1, 0, right? So in this instance, you had whether or not the number of Oscar nominations. So if a movie had 14 nominations or this many, etc., did it win, I believe, at least one Oscar? And so when your outcome is a 0, 1, often that the continuous variables or number of these trying to predict a 0, 1 doesn't work that well. There's a longer formula. We're not going to cover that formula, but I just need you to know that logistic regression is used when the outcome variable is binary, right? Or categorical in whatever way. So not a continuous variable. You're trying to predict whether something happened or didn't it, or whether you're trying to predict one of maybe 3 different, 4 different, whatever. You would use logistic regression instead. Why aren't we covering it? Because the formula is a little more complicated, and it's not as easy to do in Excel. And so I thought I'll just cut you a break on this. So that's logistic regression. I think that's all we'll need to know on that. Some other terminology: K nearest neighbor. K is the number selected, whether it's 3, 4. You map everything out on a scatter plot, all of the observations, and then based on all of the analysis you've done, whether something was classified as this thing or this thing, you've classified it as two different outcome variables. You can then in the future, see if we can get at it. Yeah. So we have our lone default, no default, and we have through a series of analysis, which includes finding a z-score versus, so it's based on their average balance, the z-score of their average balance and their age z-score were mapped out. And we know that these people here defaulted, these people here did not default, right? So if we then had a z-score of somebody in the future who would end up going right here on the scatter plot on their age and their balance, we look at this one. And if this was, if the K value was 1, meaning just your nearest neighbor, you would look at this and say, oh, this person's the closest to me. And so based on this, I'm going to predict that this person right here in this red triangle will default because that's his nearest neighbor. But K is selected based on a series of trials of accuracy. I often see 3 or 4 as the number. If it was your 2 nearest neighbors, then it goes back to the closest of the 2. 3 nearest neighbors, you take whichever one has more of. So if you look here, these 3 are the nearest neighbors it has. There's 2 no defaults and 1 default. There's more no defaults than defaults. So we would predict based on this that this red triangle would not be a default. If we did 4 nearest neighbors, you've got these 4 right here. 3 of the 4 are no defaults, are predictions that they would not default, right? So it just depends on the percentage of defaults in that range, right? So 1 is a default in this case, right? So 4 of them, you've got a 25%, 25%, 1 out of 4 is a default. So that's your prediction there, right? So whichever one of those sides it lands on, that's your prediction. So class 1, if it's 50% or higher, it's a class 1. If it's less than 50%, it's a class 0. So the tiebreaker wasn't necessarily the distance here, but if you use 2 closest, and let's say that observation 2 and 6 were the 2 closest, I'm not sure if 6 or 7 is closer, but one of those 2 is a 1. So 50%, it always goes to the 1. So basically, if you look at this, it's rounding to the nearest whole number. 0.5 rounds up to 1, 0.57 rounds up to 1, 4 rounds down to 0. So that's just a simple way of reading that chart. Just whatever new one you're trying to predict, map it out on this, and nearest K neighbors. K is a number of neighbors on your chart, but that is not known. It's up to the creator of that model what K stands for, whether it's the 2 nearest neighbors, 3 nearest neighbors, etc. You can see here the value of K can plausibly range from 1 to anywhere up to the total number of observations, as to what that is, again, up to the creator of the model as to what's working best. And I think that we're not going to get into the classification and regression trees other than definitions you might need to know for multiple choice questions. So anything from here on out in the slides, and I'm going to include the slides for you. I'm not just going to go through and read slides for you. You see a bolded term in these slides, you're going to want to know the definition. It might come up in your multiple choice quiz. Classification trees being this specific definition. Again, I don't like reading directly from slides, so I'm not going to do that for you. I'm going to include these slides, this full slideshow on the file. But again, we're looking at just definitions from here on out. Nothing we're going to go into deeply at all. Look for bolded terms is my advice here. It will help you to try to narrow down if one of those questions does come up. So that is all we have. That's it. That's the last of the lectures. We've got a quiz to do for this this section, and then there'll be an announcement about the final exam as well as the learning assessment points of your syllabus released shortly. Thanks everyone for a good semester. We'll see you around. Let me know if you have any questions.